Okay, so let's try to show or try to get the transition probabilities of this stochastic process out, and by way of that, we'll show that X is a Markov chain. And so, how do you show that X is a Markov process, or in our discrete setting, a Markov chain? Well, you start out by writing something like this: the transition on the next step to some state y, given the entire past history, right? So this is a lookout on the previous step and all the previous steps going all the way to time zero, right? The entire history of the process, and you're trying to show that this depends only on xk, right? And so we kind of can take this in two steps. We're going to try to have to fill in sort of all of these possible cases, right? And then for each case, we're going to write, what the actual events are. Like we're going to have to write y equals something, right? Y equals this, and when y equals this, it's that, and when y equals that, it's this, right? And then we're going to have to fill in all these probabilities. And if everything that we write down here for the actual probability calculations is going to depend on, if it only depends on xk, then we know that X is a Markov chain. And so what I'm going to suggest to you is that we could first start out with this sort of identification of the actual transitions, and we did a little bit of this in the previous clip, where we said, well, look, at time zero, we have to transition to 1, right? X0, the number of unmarked marbles is, the number of marked marbles is 0, and then the next step we had to pick 1, and so 1 was marked, and so x1 of 1 was equal to 1, and then we saw some randomness starting to enter, and the value of the process of time 2 was either 1 or 2, and then clearly sort of something like this keeps going, and you can almost see that xk is an increasing process, right? It's either going to stay at the same value, right, meaning that we just don't pick an unmarked marble, or we increment it, right? We increase the number of marked marbles, right? So you see that eventually all of these all of them are going to have to get marks, right? But the question is sort of maybe how long it takes, and whether what are the probabilities that this thing is actually going to approach a situation or an eventual kind of outcome with all of these marbles being marked. And so what I'm going to suggest to you is that before getting into the probabilities, you just want to list sort of what I call the transitions, right? What are the possibilities that what are the possible kind of outcomes, given that you start at whatever time you're at with precisely x, or just any kind of fixed number of marked marbles. So we start out with x, and what are the possible values? Well, we already discussed that you could stay at the same number, right, given that you picked the marked marble. So clearly x is a potential outcome, right? We could have transitioned from x to x. It's certainly possible, and it corresponds to an event, right, which I'm thinking of here, right, which corresponds to an event of picking a marble that's already marked. Or we could have transitioned to this event, which is one additional marble in the box has a marking on it. And you can potentially entertain others and say why they're not possible. Is it possible for x to go down, right, to decrement, to go down by 1? I don't see how that's possible, right? Every single time we make a pick and we add a marking, we never actually erase any markings, right? So because we never erase a marking on any of the marbles, this is not possible. Is this possible? Going up by 2. No, it's not, because we never pick out, the directions never told us that we could pick 2 marbles at once and mark both of them and put them back, right? For the same reason, this transition, x plus any I, for any I greater than or equal to 2, right, this has probability 0, right? It's not one of our transitions, and so we don't list it right there. So that's sort of the first kind of thought experiment you want to go through. And the next most important part is trying to write down what probabilities, right? With what probability does do both of these transitions happen with? And so let's think. Let's consider just one of them at a time, right? So we're going from x to x. So what actually happened? What's the event that this corresponds to? It corresponds to us picking a marble that's already marked, placing it back, and not changing the situation that was there. And so what's the probability here of doing it? Well, you have 3, 6, or 9 marbles here. What's the probability that on the next step I don't change the number of markings overall? Well, I had to pick one of these 3 and return them. So it's 3 out of 9. And in general, when we're starting with x and we move to x, it has to be x over n, right? This is the probability that we picked a marble that's already marked, thereby not changing the overall state of the system, transitioning from x and staying right to x, meaning that the chain stays in the same exact configuration. Right, and this one you get for free, right? It's just 1 minus, this. And if you want to think through sort of what it means probabilistically, you have to say, well, what event does this correspond to? Well, clearly we, added a marked marble. It corresponds to an event of picking an unmarked one, right? How many unmarked marbles are there? It's n, the total number, minus the marked ones. This is the number of unmarked marbles, and this is the number of possible choices that we had to consider. And so I see that these are the transitions and these are the probabilities, and now we can go up to here immediately and just fill in this fill in this side of the equation, right? So we have probability that on the next step we're at y, and we're going to have to go through all the possible cases on y, which are 2, right? And then the entire history, and then we're going to fill in these probabilities right here. So let's say y is equal to xk, right? This corresponds to this transition here, right? The probability is just xk over n, right? Copying directly from there. And then there's only one other case, which is y is equal to xk plus 1. That's this transition here, right? The x here I'm thinking of as the, this is what, the current time is k, and this is exactly what we consider here. Current time going on to the next step. Current time going on to the next step, right? Y is equal to x plus 1. What's the probability? It's n minus xk over n, copying directly from these 2 lines, right? So, so these are my 2 probabilities. They clearly depend only on xk, right? And all cases are covered, and you should make sure that these sum to 1, which they do. Right? All probabilities, including conditionals, have to sum to 1. Right? And from this, we essentially directly conclude that this is a Markov chain, right? This implies, this analysis that we just went through, implies that x is a Markov chain. So at this point, we can immediately skip to a calculation of the expected number of marbles at time k, and the main tool for this is going to be conditional probability, or the Tower property of the conditional probability. So here's what we do. The first step is always to write down what we're about to compute, and I suggest, because of the nature of the conditioning that we're going to carry out, you start out with, again, time xk plus 1. It matches the probability, the transition probabilities, right, the Markov probabilities that we wrote down. And the first step is always to apply the Tower property, right? This is called first step transition analysis. So you condition on the step right before, right? So there is a 1-step difference between the conditioning and the time of the original the time of the original chain, right? So xk plus 1 given xk. Right? So this is by the Tower property, right? Tower property of conditional expectation. This is always your first step, and so now the next step is always to take this expectation and sort of isolate it, right? Take it, treat it separately and try to compute out what it is, right? So this is going to be our step 1. Our step 2 is going to be the computation of the conditional probability inside. And so you can do this in 2 ways. One is you can keep this notation if you like, or if it's more comfortable, you can write it out like this. right? Whichever notation you're more comfortable with, right? This is the same exact thing, or you should get the same exact answer. So let's try to do it with this maybe slightly more basic notation, right, that you see in books. So how do we compute this conditional expectation? It's saying that we're at step k, and we're trying to look at what possible values xk plus 1 could take. Well, we know this, right? We just did this whole analysis here, right? These are the possible future values, right? And these are the probabilities with respect to which they happen. So namely, you have little x, that's one possible outcome right there, right? Times the probability with which this happens, which is x over n. Right, so this is the probability with respect to this outcome happens, plus the other outcome, which is this one right here. This is the probability with respect to which it happens. Right? And if I was doing it without this x, if I had erased this, I would just replace every little x with an xk. It really doesn't, there's no difference, right? It's just a matter of convention, notation, whatever you're more comfortable with. So if I'm to simplify this, I'm going to pick up an x squared, and I'm going to hope that these x squared terms cancel out, because we're going to run into trouble if they don't. There's going to be another x squared, I made a typo here. There's going to be another x squared coming from this part. So far it looks to me like there's an x squared over n plus an x plus 1, right? That's this part, minus an x plus 1 x over n. So now I see that this cancels with this. And eventually I'm going to get 1 plus x, that's this part right here. And this one is going to give me a minus x over n, it seems. Right? And so let me go backtrack and fill in the answer up here, maybe even up here. So I'll get 1 plus x, 1 minus 1 over n. Right? And so this goes away. And if you had done the same, and I encourage you to kind of do it maybe with this notation in place, and if you had done it with this convention, right, just by putting in the random variable into the conditioning part, which is perfectly legal and justified and fine, then the only thing that changes is that I would carry it over and adjust this little x to be my big xk, right? One thing, right, important lesson here is that a conditional expectation is nothing more than a random variable, and the randomness of it comes from this part, this conditioning, right? So a conditional expectation is a random variable in itself, and whatever's in here tells you what randomness is going to depend on, right? And so we certainly developed, right, a clear function that depends on this random quantity that this conditional expectation takes. Now that we've sort of crunched through step 2, right, we're going to continue with this breakdown. We're going to revisit step 1 and insert this in. And I would suggest maybe even, per Ross's suggestion, to write down a notation, right, for, so we're going to define this mu k plus 1 to be the expected value that we're seeking to compute. And now we're going to substitute this in here, right, lift this whole thing and put it inside the expectation. And now we just apply this this notation again, and I'll comment in a minute on the reasoning behind why this is a useful trick. Right, but the point is to always get to a recurrence equation that is describing mu k plus 1, the expected value on the next step, as a function of or in terms of the expected value on the current or on the previous step. Right? And so this just kind of, you don't have to, necessarily introduce this mu k, but it certainly kind of clears up or really highlights this recurrence nature, right? Essentially, this thing is just the expected value of xk plus 1, and mu k is the expected value of xk. It came from here, right? This is linearity of expectation, right? That's the reasoning here. This is linearity of expectation applied to get from this step to this step. And this part right here, right, I'm just applying the definition of mu k, right? Mu k plus 1 is the expected value of mu xk plus 1, and obviously then mu k is the expected value of xk, right? Which is exactly what happened there when we slid that expectation into this function. And so now again, you have this recurrence, and you know how to solve this, right? So this is this is covered in the second section. So Cosman, right, your TA will kind of go through sort of a generic way of computing these recurrences, right? Essentially anything with, anything of the form mu k plus 1 is equal to a plus b times mu k, right? You just kind of crunch out, and there are kind of, you either know the formula or you just keep plugging it in recursively until you get to the final answer. And so this is essentially how you do all of them, right? And it's important to break things down into these steps, right? First, you kind of get a sense and feel for the problem and write down maybe the steps, the state space, maybe the sample space, write those out. Then you kind of think a little bit, well, how is this process behaving in the beginning, right? Here we saw a very simple behavior right from the start. We started from x0 equals 0, then it clearly moved up to 1. By the way, that's an interesting exercise. Does this work here, right? It seemed like the very first transition was deterministic. It had probability 1. What happens when xk is 0, right? When xk is 0, this probability is 0, and this one is, n minus, is 1, right? N minus 0 over n is 1, right? So this really sums up all the cases, right? Including the time step going from time 0 to time 1. And so you play around with it, then we kind of saw what happened at time step 1. We either went to 1 or 2. We got the feel for it, and then we were able to write down, a transition in general and assign the probabilities to a general transition. And then we finally arrived at this, at these one-step transitions and saw right away that X was a Markov process. And then at that point, we know we can apply this first-step transition analysis to compute the expected value of the chain at any time, right? And the way you do it is through this conditional probability mechanism. So you write, this expression using the Tower property. I encourage you to kind of take this, break the problem down, always break things down into sort of doable steps. Take this conditional expectation, write it out, right? This took some time to kind of get this into a neat expression. And if you see an x squared term popping out, then you're toasted a little bit, right? It's sort of, there are ways to deal with those things, but not always, right? And so we really got lucky that there's this nice linear form, which then leads to a nice linear recurrence that can be solved.